आइए हम सुने विज्ञान की अनकही कहानियां.
Join us as we dive into Earth's buried mysteries with Dr. Aditya Kharya, whose studies of tiny time capsules in rocks and ancient minerals help predict disasters, uncover critical resources for clean energy and metals, safeguarding communities' future and the country's economic strength.
Myself is Dr. Aditya Kharya. I am scientist at Wihg Institute of Himalayan Geology, Dehradun. I completed my PhD from Wihg Institute itself in 2015 on fluid inclusion and stable isotope geochemistry of Ladakh accretionary prism. Currently, I am working on the geodynamic evolution of the Himalaya, especially in the Ladakh region, northwest Himalaya, as well as I am focusing on the ore mineralization in the lesser Himalaya. At present, I have focused the ore mineralization from the Sikkim Himalaya. Okay. And further, I will extend this study in the other part of the Himalaya also. Currently, I am working to know the ore mineralization, where the ore minerals are deposited, are those minerals economically valuable, whether the mining is possible, and we are trying to identify various locations of the ore mineralization throughout the Himalaya. Additionally, with the ore mineralization, I am also doing geochronology and thermochronology also to know the metamorphic evolution history of the northwest Himalaya. Basically, in the Sucha zone. Sucha zone is a part where the Indian and Asian plate collide. That is known as Ladakh plateau. So I am working in the Trans-Himalaya up north towards the Ladakh plateau, which is a part of the Tibetan crust. Somehow we can say South Tibetan crust, and to the south of the Ladakh, it is known as the Indian plate. So my work is focused on the Indian plate as well as the Asian plate. Additionally, as we all know, the Himalaya formed about 50 million years ago. Before that, there was an ocean, named as Tethys Ocean. So we have many remains throughout the world. That is a Tethys oceanic crust, which is in form of the ophiolites. And if you will see a world map, you will see several Tethyan type ophiolites. And in India, we found one of the oldest ophiolite. The age of that ophiolite is about 177 million years. So through the study of these ophiolite, we may understand what happened before formation of the Himalaya, because Himalaya formed at 50 million years. But if we will study the Tethys oceanic crust, we will know how the evolution of Himalaya will start at 177 million years. So we will connect how the Tethyan Ocean was consumed, how the continental and oceanic plate got subducted, and how the Himalaya rise. So my research area is utilized for academic purpose as well as a common man also. In terms of the academic, we can say that as I already told that I am working on the geodynamic evolution of the Himalaya. So we know how the Himalaya rise. Today we know the Himalaya is rising till date also. Somehow the Indian plates is moving towards the north. So with the movement of the Indian plates, there may be some earthquake and some type of the activity are going on like that. So we have to understand at what rate the Indian plate is moving, what happened in past, because future is a key to the past. So if we will better understand the past, then we will able to predict the future also. So before predicting the future, we have to understand the past thoroughly. We have to study our Mother Earth, what happened with the our Earth, and Himalaya is the youngest mountain chain in the world. So it is an open library, we can say. It's it is a very dynamic picture and very complex. So it is very difficult to understand how the Himalaya form, how the rocks form. Some rocks, we have ultra high pressure rock, which got subducted more than 160 kilometer depth from the surface. At more than 160 kilometer depth, they were exhumed to the surface. Whatever rock like eclogite in the Ladakh, we are seeing a black color rock, which is coming from 160 kilometer depth, and you just think how much depth it is. We are not able to drill 100 kilometer in the earth core, and the rock was subducted and exhumed to the surface from 160 kilometer depth. So this is the very complex picture in the Himalaya, which we are trying to show to the people as well as the academician also. Further, in terms of the common people or general people, we are trying to figure out the economic mineral, valuable mineral, which may enhance our economic growth. We are looking on the sulfur mineralization. We are looking for lead, zinc, copper mineralization, which may utilize in various industry. Even in Himalaya, there's some lithium deposits are also there, as well as tungsten, chromite deposits are there. So we have to be identified. Look at these, all the deposits. Where are these deposits are available? What are the concentration of these deposits? Whether they are superficial or subsurfacial. If they are subsurfacial, what is the concentration of those? So they are able to be extract and to be utilized for making lithium-ion batteries, tungsten filaments, and like copper to making a copper wire, lead, zinc. These all are the precious metals which we are trying to locate in various parts of the Himalaya, and which will be really helpful for the economic growth of our country. Yeah. My past research area, basically I focused on a fluid inclusion and stable isotope geochemistry. In the past, I have learned these techniques and try to know how the aqueous prism were formed, like how the Indian and Asian plates were collide, and how the rocks were deposited over there. They are derived from the mantle. As we know, there are mainly three parts in the earth: crust, mantle, and core. So with the help of the fluid inclusion, we will know that how they were exhumed up to the surface. From the thermodynamic modeling, we will know the peak PT condition, at what maximum depth the rock were exhumed, but in which fashion they are rapidly exhumed to the surface without cooling down, or they are rapidly exhumed without dropping the temperature, or they are uh, forming in a pattern that Tesla was not tricky. So such type of a study with the help of fluid inclusion we used to do. Additionally, we will know the composition of the fluid, which types of the fluid were present at the time of formation of the rock. As we know, the any rock formed from the hot molten material, which have some liquid and gaseous form. But anyone cannot say which gas was present on that time, whether the CO2 was present, CH4, CO, H2, what gas were present at the time of formation of that rock or that mineral. But with the help of fluid inclusion, we may able to identify and will develop a history in which fashion they were exhumed to the surface. Additionally, with the help of stable isotope geochemistry and non-traditional stable isotope geochemistry, we know the source of a rock. The fluid are coming from the mantle, or from the extraterrestrial rocks, or from the sedimentary origin, from where the fluid are coming, which is responsible for the formation of rock. That can be well understood with the help of stable isotope systematic like carbon, oxygen. Further, we do the geochronology also. In the geochronology, we may know the age of the rock, at what time these rocks were formed. For the geochronology, we use the zircon geochronology, in which we used to do uranium lead dating, and further we use the lead dating to know the source characterization, because the mantle is not a homogeneous, it's a heterogeneous. So from which part of the mantle it is, whether it is coming from a depleted mantle, enriched mantle, mob type, from which it has to be all understood with the help of several isotopic systematics. Further, at present I am working in the ophelites to understand the history of the Paleothesis ocean, which was present before the formation of the Himalaya. And we would like to give a new theory to the general audience, that how the ocean crust got subducted, how the Himalaya was initiated for the formation, and how the Himalaya was formed at the Paleocene, which is about 177 million years, because most of the research is concerned with the 50 million or 65 million. But there is a limited research which has been done regarding the Paleothesis oceanic crust. What happened before the formation of the Himalaya? It is still need to be understood. Additionally, I am working on the ore mineralization, especially in the Sikkim region, where we have identified the lead, zinc, copper mineralization, as well as some sulfur salts also. For that, we are doing the quantitative analysis. We are trying to know how those rock were deposited, how those minerals were deposited, what is the behavior, and what is the how they were formed or deposited in this region, which may further utilize for the economic purpose, mining purposes at all. And in near future, I will focus on the ore mineralization as well as to find out the precious metal like lithium deposits, chromite deposits, as well as tungsten deposits, which may helpful for the need of our country and growth of our country in terms of economical growth as well as the geology. If I talk the India ranking in this particular research area, I think it is in top 10 to 15 countries like that. We are competing with well developed countries. You can see the publication of our institute and the earth science related publication throughout the country. So we all publish in the international journals, not in local journals or like that. We are focusing the peer reviewed journal, which shows that where we are publishing. We are publishing in journals like Nature. We are publishing in journals like Earth Sciences Review, in Geology, Contribution to Mineralogy and Petrology, Journal of Petrology, or Geology Review, and many more. These all are the high reputed and high ranked journal in which the United States, UK, Germany, Italy, these are published. So we are competing with such type of the countries. We are submitting few proposals for the collaboration of the Indian institution. Myself, I have submitted one proposal on the ore mineralization, and my other colleagues, I think 3, 4, 5 projects has been submitted for the same, for the collaboration, like a private and a government partnership program. Recently, we have last published in one of our paper in Contribution to Mineralogy and Petrology. That is a very high reputed journal in which we published about the South Tibetan crust, how the rocks were exhumed, and that metamorphic rocks of magmatite that were exhumed about 19 kilometers, that is equivalent to 58-kilometer depth, and followed an isothermal cooling path. So it means they were rapidly exhumed to the surface without dropping time and the pressure, just releasing a lot of pressure and rapidly exhumed to the surface. And the rapid exhumation was evident by the fluid inclusion study, various reclusion texture like C-shape texture, implosion texture, and others. And the peak temperature, peak PT condition was estimated by thermodynamic modeling also.
This podcast series on STEM popularization is supported and catalyzed by National Council of Science and Technology, Communication, Government of India. Produced by Media for Community Foundation. Technical support is given by Soumya Mishra.